15.1.8. All the poles are in poles 0 equals 0. Poles of gamma z. I mean, you need to be specified because sometimes your textbook use gamma z plus 1 as like in the digamma function. They usually talk about z. The argument is z plus 1. So now for gamma z, the poles are this quite obvious, right? Can you see that you can see that from either the infinite limit, because all the denominator you have a z and then c plus 1, c plus 2, all that. So, and then there's also the infinite product also. The infinite product is written as 1 over gamma, but the 1 over gamma, when 1 over gamma is 0, then you get a pole in gamma. So basically, all the product term, you have 1 plus z over n, right? So it means the 0 z equals 0 and all c equals to n, all the minus integer, negative integer. Okay, so that is quite straightforward. So you got so you want the c, so c equals minus n. It's a pole. The n is now 0. 1, 2, 3, right? So this is, or you can say that this is c sub n. C equals the c sub n. It's a pole, right? And the idea to calculate the residue, the residue at c sub n is basically the function, whatever the function is, gamma z, and you multiply. Yeah, assuming it's a simple pole, so it's c minus c sub n, right? And then finally take the limit of z goes to c sub n, right? That's how you evaluate the simple pole. You remember the complex variable chapter, right? Yeah. This is how you do it. All right, so you basically just substitute this z sub n is minus n, the limit of z tends to minus n, c minus z, c minus z sub n, which becomes c plus n, right? And then you have gamma z. Basically multiply this and then that take the limit, right? We can first try the first one, see if n equals 0, see if that will give you any finite value. So n equals to 0. And so that becomes n is 0 to c gamma z. And gamma z, we already know that this is the property of the gamma function, fundamental properties. So this z goes to 0, gamma z plus 1, right? That is the property, and so that is when c is 0, this equals to gamma 1, and gamma 1 is 1. We already did that in class. You can use the infinite limit to evaluate that it is equals to 1. So we figure out, so the first residue is this is residue 0. Residue c of 0, right? Now we can see if we can find the similar way for this one. Residue of c sub n becomes limit of n Z plus n gamma z, and now we just keep doing this with repeating all this z, just this part, you know, just this part becomes this basically try to reduce it to something similar. So, and how do I do that? So z sub n basically, because this is like originally is -1, so we want to keep increasing it, so becomes, we want to get so keep this first. We want this to be z gamma z plus 1, just like what we did, right? But gamma z sub 1 is z gamma z, right? So so we need to divide it by z, right? This gamma z over z over z, right? So that the first one, and the idea is you keep doing that, finally this would be minus n, so z plus I mean I have too big a gap, not necessary, but gamma z sub 2, z plus 2, keep doing that, becomes z plus 2, z plus 1, right? Because gamma z sub 1 times z sub 1, gamma z plus 1 times z plus 1 is gamma z plus 2, right? So I express gamma z plus 1, gamma z plus 2 divided by z plus 1, right? And so I keep doing that. You know what I'm doing, right? So keep doing that. Equals to finally we will get z plus n. Each time it increase by 1, right? Each time it increase by 1, and what we want to get is 1, because z0 is singular, so we want to get to 1. So c in z finally we take the limit of minus n, so we need the n plus 1. We need gamma c plus n plus 1, right? Because that later on we take the limit. This is minus n, so that becomes 1. And so now we figure out how many factor here. Let's see, c plus 1. So this first, and all the way to finally the last factor is 1 less than that. So if this is c plus 2, this is c plus 1. If it's c plus n plus 1, this will be c plus n. Is that true? Yeah, right. That's fine. And that is the final trick. So I probably should add another term, c plus n minus 1, and then c plus n. Right? You get this up to here? And the reason this is a trick, because we already have a z plus n here. So now finally allow us to cancel that. Right. Now, after you cancel that, you can take the limit safely, because you just, z is going to minus n. All these are not singular, right? You just just substitute. I mean, take the limit now. So c is minus n. So it's c1. And now you need to be a little careful to see what those are. So minus n, the first factor. The second factor is minus n plus 1. and all the way to -1. Right. And now, how many of this? Because this is 1 and to c minus 1, right? And so that's n minus 1 factor, and then you extra z terms, so totally n factor in here, right? And start from n, so all n to 1, so n factor. And what you can do is take all the minus sign out, becomes a -1. You have n of them, -1 to the n power. And then gamma 1 is 1. And finally, this is n. Just flip all the sign, and -1, and -2 all the way to 1. That's n factorial. Right? Is okay? So that could be just the alternative way, other than your textbook derivation. Is the textbook derivation is still valid, but this is another way to do this. Is okay? So.